So make sure you're doing the seating chart and make sure you've checked in on iClicker. I'm prepping it so I don't have to write so much when we get there. That's where we're picking up today. Got 2 more minutes. Trying to remember the jokes from today. It's a different one every day, so I always have to remember. So you're doing your seating chart. We got 1 more minute. Okay, so what do you get when you cross a turtle and a porcupine? A slowpoke. What kind of pants do clouds wear? Thunderwear. So good today. All right, so make sure that you've put your name on the seating chart for today, please, and that you are on the right date. So make sure you're on the right date. The other thing I want to point out before we even start class is today is the 19th. So what do we have next class period? An exam. So you'll be in here taking the exam on paper with a pen or a pencil, and you will bring a calculator because I will not have extras. If you do not bring a calculator, you will not have a calculator for the exam. So bring your calculator, bring your pen or pencil. I provide everything else. I will give you a paper exam. I will give you an answer sheet, and I will give you a best friend. Okay? Good? Questions about that? Okay, if you are online, if something happens, whatever it is, I put this new little tab on our class Moodle page. It's the Respondus. If something happens for any reason and someone has to take an exam online, you'll take it on Moodle and you'll use Respondus. And so this is a practice exam just to make sure that it's not really an exam. It's like what's 2 + 2, you know, just so that you can practice using the system if you are online. These are the instructions. You have to download some things in order to be ready to go. So this is just for someone who is completely online. Any questions? It doesn't count for points. You could take it as many times as you want. It's just to make sure like your system is working, your webcam is working because it's monitored with a video, that you know what it's going to look like. You know how you're going to access your best friend. It's just so that you've seen it once before you actually have to take the exam. It kind of eases your nerves a little bit, I think. Yes, it is going to be your exam in person. You are here. I'm handing you the paper. It is your paper. Write all over it. Write anything you want on it, as long as you know it's not rude, crude, or socially unacceptable. Go for it. You know, get your paper and start jotting down those things. Remember, every now and then I tell you, oh, this would be a really good thing to memorize, right? Like delta G, delta S, delta H, all that kind of stuff. You can put that, you can add that to your best friend. Yes, it is multiple choice. It is all multiple choice.
How many questions?
That depends today. Depends on today. We're gonna see how far we get today. So it's still a work in progress because I don't know exactly where we're ending today. So whatever we finish today will be on the exam. Whatever we do not finish will be on the next exam. Okay? Any other questions?
Are you gonna have like a review, like if you have questions like we did last time, or like is that first way?
No, this is so that was because we had a hurricane, you know, that was a whole class period because we had a hurricane. So I'm not doing that for this one. Okay. All right, anything else? All right, let's get started. Okay, so get your eye clickers out. Get those eye clickers out. Get your calculators out. You never know, you might need that. Trying to remember for this one if you do. I don't think you actually do. Okay. I'll do this. All right, so here we go. Let me see if I can move the chat box. Okay. In general, in a general chemical equation, where are the following 3 components located? The first column will be the first thing, the second column will be the second thing, the third column is the third thing. So pick the answer choice that puts them in the correct order. So we want a general chemical equation, and tell me 1, 2, 3. Remember, you get 1 minute. Okay, 5 seconds. Okay, turn, talk to the people around you, make a second answer. People in the chat, you're welcome to chat about it. 30 seconds. I don't think this one should take you long. Okay, don't forget to check back in again. 10 seconds. I think we had 40, was it 41? I always try to look and then I always forget. Okay, looked like 41. All right, so almost 100%, very close. So D is correct. Remember, when we have any given chemical equation, we go reactants And then we have a yield sign, which is the little arrow, and that goes to products. So let me go back. I think I didn't grade the first one. All right, good. Okay, so what are three? We had A and B. Yeah, so you knew the yield sign, but it's always reactants, yield, products. That's the path of every single general chemical reaction. Okay. In an exothermic reaction, heat blank. In an exothermic reaction, heat blank. One minute. Ten seconds. Okay, turn and talk to the people around you. 30 seconds and you can buzz in again. Okay, 10 seconds. Make sure you've buzzed in again. I say buzz in, click in, whatever it is. Okay, here we go. All right, so in an exothermic reaction, heat, good, is given off by the reaction. Good, good, good. All right, so I was really easy and nice to you here because what term did I use in the question? Heat, right? If this says exothermic reaction, could I say energy is given off? Can I do that? No, no. What would be, well, there's thermic means heat. Thermic is heat. What's the equivalent for energy? Yeah, the energy, right? What is it? Genic. Right? So make sure that you're looking at that root and make sure that you know which one you're talking about. Okay? So be very careful about that. All right, let's see. Okay, I think we got two more today. I think we have a few today. All right. So in an energy diagram for a reaction, the products are shown at a higher level than the reactants. I would sketch that right now, right in front of you. Sketch an energy diagram like we did in class, where the products are shown at a higher level than the reactants. What must be true about this reaction? Remember, 1 minute. Ten seconds. Make sure you buzz in and answer. Okay. Turn and talk to the people around you. Buzz in again. I still hear some chit chat and I'll give you out till 45 seconds. So everybody buzz back in your second answer within 45 seconds. 10 seconds. Okay, so what did you sketch? I'm curious, what did you sketch? Something that looks like this, and it goes from reactants to products, right? That's the order. And what did you put on the other axis? Energy, right? Some Gibbs free energy, some kind of energy. Okay, and then you sketch the products shown higher than the reactants. That's why I like to put products and reactants down at the bottom, because I can just do that. So I can say products are higher than reactants, right? So what were you automatically, let's see how our results look. Uh-oh. Uh-oh. Okay. So what can we automatically cross out? We're talking about what part of science? We're talking about heat, or are we talking about energy here? Energy. So which answer choices can I immediately cross out? I can immediately cross out B. I can immediately cross out C, because delta H is what? Heat. Am I talking about heat? No. Okay, so A talks about energy, D talks about energy, and E talks about stability. Well, I haven't discussed stability yet, so I'm not even going to talk about that, right? So does the reaction absorb energy to form products, or is our potential energy decreasing? So I'm low energy. To become products, I have to be high energy. So do you have to put in energy to form the product? Yes, this is Dr. B. Let's put a frowny face, a sad face, that she has to ride the bike all the way up the hill. Oh, that's so terrible. I have to put in so much energy. So this reaction has to absorb energy to form the products. So it has to be A. That's so sad. You don't think they're right? Oh, here. Oh, because I already graded those. Those are the ones I graded. Okay. Oh, that makes me feel so much better. Y'all are so awesome. Yay. That's so much better. Okay. Everybody feel better now, right? Okay. All right. So let's go on. One more. All right. Select the correct statement regarding the reactions represented by the energy diagrams. This one you kind of have to think about. Eliminate the answer choices you know you can eliminate. Careful about that. And always picture Dr. B riding her bicycle. Okay, y'all buzz in. Let's close it at 1 minute. 10 seconds. Try to always give you a warning. Okay. Turn and talk to the people around you. Okay, you have to cover your mouths and noses with your mask while you're talking. Y'all, please, in the back of the front. Ladies. Thank you. I'll give y'all till 45 seconds. Make sure you buzz in again. 45 seconds. Okay, almost. Everybody buzz in. Okay. So what did we say? Oh, let's before I even look, what were you able to eliminate? Very nice. A and C, we just eliminated those. Now, all the other ones talk about the rate of the reaction, right? B is slower. I'm sorry. B is saying reaction A is slower. D is saying reaction B is slower. And E is saying the reactions are equally fast. Look at the reaction diagram and put Dr. B on her bicycle at the bottom of each hill. Which one do you think I would rather ride? I would much rather ride B. So I'm going to be a little bit happier. I'm going to be a little bit sadder, right? Which one do you think is going to take me more time to climb? It's going to take me more time to climb. So my reaction A should be slower. So what did we get? Let's see. B, good, very good. Awesome. Okay, I like that every time we do this, you increase. It's very nice. All right, so how about we go back to lecture? How about we go back to lecture? Always think about Dr. B on her bicycle. Okay, this is kind of where we left off, right? Oh, I need my best friend over here. Okay, so I think I did put it on there. Look on your best friend. Do I give you your conversions? I don't. I was looking to see if I gave you this, but I will give you this on the exam. If I don't already have it on the best friend, I'm going to write myself a note to make sure that I have these conversions right here. This will be on your best friend. I'll call it on your BFF, right? So I want the caloric values. This is table 5.1 because it's not on the best friend that I printed, but I don't know how old this best friend is. Can y'all look? Is it on the one that's online? Anybody see? I don't know if I gave it to you or not, but I want to give it to you. It's not on there. It will be on there by Thursday, not Friday, Thursday. It will be on your best friend. Okay, so remember how we said that there are different classifications of biomolecules that we eat, right? We eat carbs, we eat proteins, we eat fats. And on food labels, right, they break that down for us. They tell us how many grams of each that you get in the foods that you're consuming. Now, it's really important. Did we talk about this for patients who are diabetic? Did we talk about this? No. Yes? No? So if someone's diabetic, what's the problem? Their body either does not make insulin or their body is unresponsive to the insulin that they do make. It's two kinds. So why does your body make insulin in the first place? It's regulating your blood sugar. So if your blood sugar gets high, your body releases insulin. Insulin is a hormone that tells all of the cells of your body, hey guys, there's sugar in the bloodstream. You need to take it into the cell so that you can use it for energy, right? Now, if you make insulin and your blood sugar goes up, insulin will be made, your bodies will respond to the insulin, and what happens to your blood sugar? It goes back down, which is great. If you're diabetic and you eat things that have simple sugars, like carbohydrates break down into simple sugars, your blood sugar will go up, but you're not making insulin. What happens? You could go into organ failure if your blood sugar stays up too high. So what do diabetic patients do? They give themselves shots of insulin or an insulin pump, right? But you have to know how much insulin to give, right? Because if you give too much insulin, your blood sugar will tank, and that's just as bad, right? You'll go into a coma. It's not good either, right? So you have to give yourself enough insulin that'll bring your blood sugar down, but not so much that you'll have no blood sugar, right? So counting carbohydrates is really, really important for diabetic patients. But regardless of what foods you consume, there's energy inside of those foods. But the different foods have different caloric values because of how they're made, because of how they store energy. And we'll talk about all these as we keep going in the semester. So carbs and proteins will each give you 4 calories per gram. That's big calories, right? Remember we showed the difference between big C calories, which is nutritional, calories, which is science, which is chemistry, right? And then joules. And then we have what? Fats, right? So if we're given this, what we can do is we can take any given meal, for example, 5.12, how many calories, big C calories, would be found in a breakfast consisting of 2 eggs, 2 pieces of toast buttered with 1 tablespoon of butter, and a 1 6 fluid ounce glass of orange juice. So what we need to do is go and find out how many calories are there in each, right? So tell me about eggs. What do we have in eggs? Go and look up at the table, right up at the top, and go and find the food. We go find eggs. This is for 1 large egg. It tells me how many grams of each carbohydrate, protein, and fat. Now, they were really nice and they gave you calories here in parentheses, but I'm not always going to give you that. So I don't want to go off of this. I'm not going to give you this on an exam. I won't give you this column. Don't use it. Okay, so if I come down here, I say how many carbs were in eggs, 2 eggs. What are you going to tell me? 1.2, how did you get 1.2? Because that's not on the list. It was 0.6 carbs per egg. So I got to multiply that times 2 to get 1.2. That's right. Okay, how about protein? So you've got 6.07, you multiply by 2, you got 12.14. How about fats? I got 5.58. Is that what y'all got? Times 2, you get 11.16. That's just your eggs. And this is all in calories. So we'll put a big C behind it. So all of these numbers are in calories. Okay, how about your toast? How many grams of carbs? How many grams of carbs? 28.2, because you had 14.1 times 2. Okay, how about protein? 4.8 from 2.4 times 2, you get 4.8. Y'all doing the math, right? Okay, what do you get for fat? 0.9 times 2, 1.8. That's all grams, right? Okay, now how about butter? Do you have a lot of carbs in butter? 0.008 I get. 0.008. Y'all find that on the chart? Okay, how about protein? Oh, because it's 2 tablespoons, we got to do times 2, right? 0.0616. Sorry about that. So what do you get for butter? Oh, butter is 1 tablespoon or 2 tablespoons? It's 1 in the question. Let's see how much they only put 1. Okay, so it is only 1. Sorry. Okay, so now in 1 tablespoon of butter, how much protein? 0.12. How much fat? So butter is mostly what? Fat. Butter is mostly fat. Eggs are protein and fat, right? Because you got the yolk and the white. Okay, OJ, it said it was 6 fluid ounces, but in your table it only shows you by cups. So you had to convert 6 fluid ounces to cups. So I already did that for you. And 6 fluid ounces is the same thing as 0.75 cups. So in 0.75 cups, how do we figure that out for orange juice? You would take the value for 1 cup. What's the carbohydrate grams for 1 cup? 27 grams, but we only have 0.75 of a cup, right? So multiply it times 0.75, what do you get? $20.25. So we have to do the same thing for our protein. How much protein do you get? Only 2 grams, but that's for a whole cup. So we got to multiply that times 0.75. What do we get? 1.5. How many grams of fat? 0. Okay, so now what I do is I get all of my totals for each of my categories, and then I'm going to convert that to energy, right? So how much total in my first column carbohydrates do I have? Add them up. 1.2, 28.2, 0.008, 20.25. What do you get? 49.658. And do you round at this point? No, because you're not done. So this is grams. Do I want to be in grams? No, not really. What do I want to be in? What are they asking me for? How many calories? So what do? I need a conversion factor that will put me grams and big C calories. Do I have one? Go look up at the top. Do I have one? Do I have something that's going to tell me calories in grams? Yes, so I know for carbohydrates, there are 4 calories per gram. So put it down here, 4 calories per gram. Right, so what do we get? I'm just going to do this. I'll put the total down here. What do I get? 4 times almost 50, should be almost 200. 190. Yes. So what are my units on this? Because my grams canceled, what do I want? Calories. And some people put them as CAL. I just like to do the big C. That way I know the difference between nutritional calories and science calories. Okay. All right. So how about a total for proteins? What did you get? Total up everything in your protein column. I should hear lots of calculator clicking. Lots and lots of calculator clicking. 18.56 grams. But this column is proteins, right? So what's the conversion to proteins? It's still 4. It's still 4. So my grams are going to cancel and I'm left in calories. So what do you get? 74.24 calories. Okay. The last one, total up the fats. What do you get? 4.26. And now, what's my conversion here? Be careful. This is 9 calories per gram. So my grams are going to cancel. I'm left in calories. How many calories? 14 big C calories. So what's my sum? What's my total from everything? Add all 3 together because I want my total calories for the entire meal. So this is an entire meal. $400. Give me all the digits and then we're going to round. Okay, so now what do we round to? Let's come back up. How do we know what to round to here? Technically, how many significant figures do I have? Only one. So round your answer to 1 sig fig. 500. So that's a 500 calorie breakfast. Pretty big breakfast, right? So if you're diabetic, you're only really counting carbs. You're not counting everything, but you should be able to do that. Now, can you convert this to calories? Just want to know if you can. So you might have to do that on the exam. What do we know? One nutritional calorie is equal to 1 kcal. What's a kcal? A kilocalorie, right? So that would be 1,000 calories, right? Okay, how do you convert that to joules? Like I might ask it for you to you in joules. Go to your best friend, and your best friend has a conversion. 4.1. So which one is it? Is it joules or calories? Where do I put the 4? Look on your best friend. Let's see, where was it? Was it at the top? Yeah. So kind of towards the top. So you put it with the joules. Do you see how it's with the joules? 4.18. What is it? 4.84. 184. 4 joules per calorie. So then you can convert it to joules or kilojoules or whatever it is. Do you still have to be able to do conversions? Absolutely. Don't forget that skill. Okay. But this was technically the answer to the problem, 500 calories. I just wanted to make sure you could still do that. Okay. So we're going to back off from the math a little bit, which I think y'all are going to enjoy. Yeah, see head nodding. It's all good. All right. So when we talk about chemical reactions, remember how we were talking about, well, this reaction was faster than that reaction, right? What controls that? Now, when I talk about kinetics, I like to use an analogy with cars on the road, right? So let's talk about cars on the road before we talk about chemical equations. What happens when there are lots of cars on the road, like really heavy traffic times? What happens often? Wrecks, accidents, right? Okay, what happens when people speed? What do they get into? Accidents, wrecks. Okay, so chemical reactions are really just wrecks. It's when atoms collide or molecules collide in order to induce a reaction to happen. Now they have to collide in a perfect orientation for it to be a fruitful collision. But chemical reactions require a collision. So when we think about temperature, what happens to molecules as we increase their temperature? What do? They speed up, they go faster, just like the cars on the road. So if the molecules go faster, what do you think is going to happen to those molecules? There are going to be more collisions, just like on the street. Okay, what if we have a greater concentration of molecules? Are we going to have more collisions or less collisions? More collisions. So it's just like cars on the road. Okay, so how does increasing the temperature increase the rate of a chemical reaction? Well, if you increase the temperature, you're increasing the speed. You have a higher number of collisions, so your reaction rate goes up. See how that perfect analogy works with the cars? Hey. Okay, how does increasing the amount of reactants, this is concentration, increase the rate of a chemical reaction? You have a higher concentration, more collisions, higher reaction rate, right? Okay, so when molecules collide, there are two things that have to happen. In that collision, the collision has to be at a perfect orientation. And the collision has to have enough force, enough energy in order to make the product. You can have collisions that are non-productive, right? It's just hitting the wrong part on the molecule, right? The molecules aren't in the same orientation. or the molecules collide and they just kind of bounce off of one another. They don't actually form a product. So our activation energy is the energy that's required to make that reaction go. If you don't have enough energy, no reaction is going to go. Every reaction requires some amount of energy. So our activation energy is the minimum amount of energy required to go, but that's a terrible way to say it, right? You know, you understand what I'm saying when I say that, but we have to change our vocabulary a little bit. It's going to be the minimum amount of energy required to overcome what's called the energy barrier. Overcome the energy barrier between our reactants and products. So there's every reaction requires a certain amount of energy. That's the energy barrier. And once you go over that energy barrier, now I can convert reactants to products. Does that make sense? Okay, B. Now, how does adding a catalyst increase the rate of a chemical reaction? So do you remember when I showed you this energy diagram? And when I drew the line that connected them, I made this little hump. I remember that? And you're like, that looks bizarrely weird, right? Well, this right here is the activation energy. The energy required, they call it the EA, activation energy. Energy required to go from reactants to products. So what does a catalyst do? Picture me on the bicycle. Right? I'm pretty sad right now, right? But what if I had that same reactant, the same product, the same place on the lines? I still have a hill to cross, but in this case, I'm going to add a catalyst. And that catalyst is going to drop that hill for me, right? This is what a catalyst will do. So this is plus a catalyst. So my catalyst did what? I had an activation energy that's pretty gosh darn high. From here to here is my activation energy. I dropped that activation energy by quite a bit by adding a catalyst. Do y'all see that difference? So that's what a catalyst will do for me. It will reduce the activation energy of our reaction, It makes it a smaller hill to have to climb, an energetically smaller hill to climb, which makes progressing from reactants to products easier. So if you have a slow chemical reaction, are we going to have a large or small activation energy? If we have a slow chemical reaction, picture me on a bicycle, right? Here and here. This has a high activation energy. Picture the same things, but I've made the hill smaller. So we're going to have a very high activation energy because this is a slow reaction. This is slower. This is faster. What? Yeah? No? Okay, so picture me on a bicycle, right? So this is A, this is B. Which one do you think I want to do on my bicycle? I want to do B. Why do I want to do B? It ends up, I will complete it faster. If I put the same amount of energy in, I'm going to complete it faster. But why would I want to do B? It's less energy. I have to put in less energy to go from reactants to products. And that's something that has, this one will have a lower activation energy, right? Here's my activation energy. This is the maximum. Here, my activation energy is all the way at the top. So I have a higher activation energy for A than I do for B. Correct. Correct. Yes. Yeah. So the higher the hump, the higher the activation energy, the slower the reaction goes. The lower the hump, the lower the activation energy, the faster the reaction goes. Okay. All right. So enzymes, which are catalysts. Another word for enzymes, AKA catalysts. Right? Enzymes function as catalysts. So they're basically used interchangeable. Increase the rate of a chemical reaction by lowering the activation energy. Here's another reaction, right? The orange one is uncatalyzed. The blue line is catalyzed. What happened to the activation energy? My activation energy went down, right? So it's going to increase the rate of our chemical reaction because we decrease the activation energy. Yeah. Okay. In an enzyme, the location where catalysis occurs. Catalysis is the actual chemical event where you're changing one molecule into another molecule. So where on the enzyme does this happen? This is, you probably learned this in biology. Maybe like a lock and key enzyme. You heard that before? Maybe. It's called the active site. Right? Like you have a really big old molecule that acts as an enzyme, but there's only one place on the molecule on that enzyme where it actually interacts with the substrates, and that's called the active site. Okay, so let's see if we can predict some things that will happen. Determine if the following changes in condition would increase or decrease the rate of chemical reactions in which they are involved. So adding a metal surface for two reactants to locate each other. So if you have a solid metal, and this solid metal is allowing the two reactants to come and sit on it and get in close proximity to one another, what do you think? Is that going to increase or decrease the rate of our reaction? Increase. We're going to increase it. This is an example of a catalyst. This is an example of a catalyst. Not all catalysts are enzymes. Some catalysts can be metals. Okay, B, decreasing the amount of one of the reactants. Is this more cars on the road or less cars on the road? This is less cars. This is you going to work at 4 a.m. You're going to get into an accident at 4 a.m. Let's say you're awake. Let's pretend you're awake. You're not on your phone. You know, there are just less people for you to get into an accident with, right? So if you have fewer molecules, if you decrease the concentration, have y'all seen brackets for concentration? Have you seen that before? So anytime you see something in brackets, brackets means concentration. That's a chemistry thing. So if I decrease the concentration of reactants, what's going to happen? I'm going to decrease my reaction rate. Okay, C, caramelizing onions on a medium-high stove setting versus a low setting. What did you just do? Increased what? I increased temperature. I went from a low setting to a medium high setting. So do you see how my temperature went up? So if my temperature goes up, what's happening to those molecules? Right? So that you have increase in the molecule movement. That's what temperature is. So if we increase our molecule movement, what are we more likely to have? Increased collisions. If we have increased collisions, what happens to our reaction rate? We increase our reaction rate. Yeah. These problems are pretty easy. I would definitely go and do the extra ones that are at the end of the chapter, right? They'll be really good extra practice. Okay. Remember how we balanced chemical equations, however long ago that was? So we're gonna do a little bit more of that today. But before we do that, what we're going to talk about are the different kinds of reactions that can actually happen. So I know I kind of have it at the top, but I want to do it again. Let's do it up here. So you can have synthesis reactions. If you have a synthesis reaction, what do you think you're doing? You're creating something new, right? So we have X plus Y. And what are we going to make? XY, right? XY. You can have decomposition. Using X and Y, how would I write that? Use the same symbols that we used in synthesis. XY yields X plus Y. Do you see how they're opposite of one another? Synthesis is the opposite of decomposition, right? Decomposition is breakdown, synthesis is creation. So it's just the opposite of one another. So if you're looking at decomposition, you're looking at one thing turning into multiple things. If you're looking at synthesis, you look at multiple things turning into one thing, right? Exchange. Exchange reactions occur when you have two AB plus CD. When you have two things already there, right? So we have two different compounds. Those compounds are typically ionic compounds, right? So you have like a metal and a non-metal. Your metal is A, your non-metal is B. Your metal is C, your non-metal is D. And then what happens in here is, watch, I'm going to do this. I'm going to say these are, my non-metals are blue. I'm sorry, my metals are blue. My non-metals are red. So what happens in an exchange? They trade partners. So if A normally partners with B, what's A now going to partner with? D. If C normally partners with D, who does C now partner with? B, right? So now I still have, here's my metal and here's my non-metal, right? So I still have a metal and a non-metal, a metal and a non-metal, a metal and a non-metal, a metal and a non-metal. Yeah. So you'll see that a lot of times in exchange. There is a particular type of exchange that you need to be able to recognize. This type, so this is a type of exchange, and it's called combustion. Everyone's favorite reaction, right? So in combustion, do you remember when we said you set off dynamite? You take a solid and you turn it into gases, right? Okay, so same sort of thing, same thing that happens in your engine. You are always going to produces carbon dioxide. What's the symbol for carbon dioxide? CO2 and water. So if you have an exchange reaction where you are producing carbon dioxide and water, that is combustion. So let's look at A. What profile does A fit? Synthesis, decomposition, or exchange? Synthesis, because I'm taking two individual things, my nitrogen and my hydrogen, these are individual, and I'm making a new compound. So this one is synthesis. Could you write this on your exam, on your best friend? That would be a good thing to write on your best friend. I'm going to put write on exam /BFF. Okay, how about B? What's happening with B? I have two reactants and I have two products. It is a type of exchange. What kind of exchange? It is combustion. Okay. So usually it's a hydrocarbon with oxygen, and then you get carbon dioxide and water. That's typical combustion reaction. All right, now how about C? What's happening in C? Aluminum's a metal, potassium's a metal, right? My SO4, that's a polyatomic. My OH is a polyatomic. They're nonmetals. So what happens is they trade partners, right? So the aluminum now interacts with the hydroxide, and the potassium now interacts with the SO4, right? So what kind of a reaction is it? Exchange. Yeah. Some people call them double displacement. You might have been taught that in high school, but it's double displacement or single displacement. They're still exchange reactions. Okay, so when we talk about chemical reactions, we've talked about we're going from our reactants yield products, right? That's a general overall chemical reaction. But this, the way that I wrote this, tells you that all of the reactants turned into products. And that doesn't always happen. Lots of reactions are what's called reversible. So if I have a reversible reaction, my reactants can go to products, but the reverse can occur as well. My products can convert to reactants. So I have to say it can go in the forward direction and it can go in the reverse direction. So when you're trying to analyze, is it reversible or irreversible? All you have to do is look at the arrow. So the first one that I drew, is that reversible or irreversible? IBLE, irreversible. So this is saying that once that product is made, it can't go backwards. It can't turn into a reactant. But in my second one that I drew, I'm saying that a reactant can turn into a product, but a product can do what? Go back to a reactant. So this is a reversible reaction. So these are like the easiest problems you're going to come across like the whole semester. So look at A, reversible or irreversible? This one is reversible because it has the double-sided arrow. Okay, how about B? Irreversible because it has a single arrow forward. What type of reaction is this in B? B is an exchange, and that kind of exchange is combustion. If you make something combust, if you light it on fire and explode it, is it going to revert back to its initial state? No. If you put gas in your gas tank and you burn it, are you ever going to get that gas back? No. That's an irreversible reaction. Okay, look at C. Tell me about C. Reversible or irreversible? It is irreversible because it has a single arrow forward. Okay, so a lot of times it's that you can't get those products back. All right, so the next thing is we are going to balance some equations. The same rules apply when you're balancing combustion in particular, that just the same rules as we had before, right? Count how many atoms on one side, how many atoms on the other side, they have to equal. But I'm going to tell you that if you balance them in a particular order, you are going to have less work to do and it's going to be easier. So balance your carbons, your hydrogens, and your oxygens. Okay, so this is the order to balance: carbon, hydrogen, oxygen. Write that down. That is the order that you want to balance in. And sometimes they will give you the products and sometimes they will not. So this says write the products and balance the following reaction for the complete combustion. If you have a partial combustion, you'll have other products. But if you have a complete combustion, you will only have CO2 and H2O as products. By definition, that is a complete combustion reaction. Okay, so let me write this a little bit bigger so we have a little bit more room. Okay, so we have C4H10, and I'm not going to write in the states of matter just so that I have a little bit more room. O2 yield, is this reversible or irreversible? Irreversible. What are my two products? CO2, H2O. Okay, now I need to balance these chemicals on either side of the equation. What order? What's my order? Carbons, hydrogens, then oxygens. So carbons, I have 4 here. How many do I have over here? 1. So what am I going to do? I want to multiply by 4. So I'm going to put a 4 here. Okay. Now what do I have to do? Hydrogens. Hydrogen on this side is 10. Hydrogen on this side is only 2. So what am I going to do? Times 5. And I get 10. I think I didn't write that. Okay, so I'm going to put a 5 there. Now what? Oxygen. So on the reactant side, I have 2. On the product side, now be careful. 4 times 2. 4 times 2 is 8. 4 times 2 is 8. 4 times 2 is 8. Okay, now 5 times 1 is 5. So how many do I have total? I have 13. Okay, so what do I do? So, okay, here's the deal. Do you see how this is an odd number and this is an even number? Am I ever going to make that happen? No. So what do I need to do? I need to what? Multiply it by 2. If I multiply everything by 2, this odd number becomes even, right? So let's do that. Let's multiply everything by 2. So what's in front of here? C4H10. It's really a 1 there. So multiply everything times 2. So 1 times 2 is 2. We don't know what to put here yet, so we're going to leave that blank. 4 times 2 is 8. So I'm going to convert that to an 8. 5 times 2 is 10. So I'm going to convert that to a 10. Now let's go back and recount. Carbons. How many carbons on this side? 4 times 2 is 8. Carbons on this side. 1 times 8 is 8. So that checks out. Hydrogen. 2 times 10 is 20. Over here, hydrogen. 2 times 10 is 20. That checks out. Okay, now my oxygens. 8 times 2. Let me just erase this. Okay, let's see. Okay, so 8 times 2 is 16. And then I have to do 10 times 1 is 10. So what do I get? 26. Can I multiply 2 times something to get 26? So I'm going to put a 13. So the trick is when you see something that becomes odd, you just multiply by 2. And it works. It works, it works, it works. Questions? Practice. Practice, practice. Okay. So we are going to talk about a bunch of different reactions, a bunch of different kinds of reactions. And up until now, we've kind of shown every single part of every single molecule that participates in a chemical reaction. But when we get to biochemistry, how the body really works, you don't have to show the entire molecule because typically the entire molecules are huge. And so what we end up doing is only showing parts of the molecule that are important for the reaction. So I want to compare 5.27 and 5.28 because there are three different kinds of reactions, right? We have chemical equations used in organic chemistry, biochemistry, and general chemistry. So I guess we really technically have three, right? We have organic, bio, and chemical. So when we talk about the difference between organic and biochemistry, we're always going to show a structure for reactants and products because a lot of times structure is very important in determining how things are going to interact. Remember when I had you learn all those functional groups that are going to be on the exam on Thursday? Remember that? You're studying those, right? On the Quizlet, something. A lot of times, if you look at functional groups, it's functional groups that interact with one another. So if we show the structure of the functional group on molecule 1 and we show the structure of the functional group on molecule 2, we end up knowing what kind of a reaction is going to happen. So we have to show some kind of structure for both reactants and products. We're always going to have a yield arrow, no matter what kind of equation you are, all of them, so all have a yield arrow that tells us, is it reversible, is it irreversible? And we're going to have to balance organic and biochemistry and general chemistry equations. So all are going to have a yield arrow, and we do need to think about balancing and balancing. And balancing. But there are some differences. So when we talk about, right, we're going to say general. When we talk about general chemical equations, so just like what we did with combustion, did we show the structure in general? Go back one. Did we show any of these structures? What did we show? What are these called? Formulas, molecular formulas. So in general, we show molecular formulas, right? Whereas in biochemistry and in organic, it's not just the formula that it's important. It's actually the structure / functional groups. So we have to visualize those things that are going to be interacting so that we know if a reaction is going to occur or not. Before, in general reactions, we just look at the formulas and say, did it substitute? Was it a combustion? Right, all that kind of stuff. But now we have to really start looking in organic at the structural or functional groups. Okay, so those are the big differences. So one type of reaction that you have to get really familiar with are called oxidation reduction reactions. So this is something right here that you need to memorize. Okay, so when we talk about things that undergo an oxidation reaction, have you ever seen like your banana? What happens when you open your banana and you walk away from it? It turns brown, right? Turns black. That's an oxidation reaction that's happening. So you have it coming into contact with oxygen in the air, and then components within the banana itself are actually oxidizing. So what's actually happening to that banana? Either it is losing electrons. So the way that I remember this is oxidation. This is how I write it to remember it. Oxidation is loss of electrons. It is a gain of oxygen. See how the O and the O? Oxidation is loss of electrons, gain of oxygen, or loss of hydrogen. But if you remember that oxidation starts with what letter? O, you're gaining oxygen. Okay, oxidation is loss of electrons, gain of oxygen, loss of hydrogen. Reduction is the opposite. So it's be a gain of electrons, a loss of oxygen, and a gain of hydrogen. You're looking for one of these three characteristics in order to classify a reaction as an oxidation reaction or a reduction reaction. I have a little mnemonic for you to remember the electron part. Have you heard this before? Oil rig. So this tells me oxidation is loss of electrons. Reduction is gain of electrons. So if you remember the oil rig, and then you remember O for oxidation means you're gaining oxygens, you got them all. There are some other little mnemonics you might have learned in high school, but this is the one, these are the ones that I like. Okay. Oh, so I gotta go to the next one. Y'all ready? Y'all wrote this down? I'm gonna pause. Some people are writing down. What's that? Y'all got it? Okay. All right. So we have to be able to look at substances and we have to be able to classify them. Are they undergoing oxidation or are they undergoing reduction? So let's look at them and then let's kind of write. Do I have room to write at the top? Not really, but I can kind of create some, right? So let's put our little thing at the top. Oxidation is what? I'm too close to the top. It doesn't want to recognize. Oxidation is OIL is loss of electrons. What else? Gain of oxygen or loss of hydrogen. And then all you have to remember is reduction is the opposite of that. Okay, so silver ions, which means you're starting with Ag plus, are electroplated as silver atoms on flatware. So how would I write a chemical reaction for this? What is the starting material? The ions are charged, right? And they are turning into what? They are turning into atoms. So how do I write that? That's a silver atom, right? An atom is uncharged. Okay, now let's talk about this. What is happening? And usually we put it as if you put a solid, the solid's uncharged. What is happening in order for this transition to occur? If I'm a +1 charge, tell me about my electrons. I have less electrons than protons, right? Now, what happens when I convert to the neutral form? What did I do? And when I go this way, I gained 1 electron, right? If you go from a +1 charge to a 0 charge, how did that happen? All you can do is gain or lose electrons when you change charge. That is the only thing that you can do. So if I go from a +1 to a 0, that means I gained an electron. So how could I classify this reaction? If oxidation is loss of an electron, what is gain of an electron? Reduction. Yeah. Okay. B. D-glucose reacts with hydrogen to form the sugar alcohol D-sorbitol. Do you have to know the structure or the formula of any of this? No, not necessarily. So let's do it without writing any formulas. So I'm going to have D-glucose reacts with hydrogen. How do I write that? Hydrogen never exists all by itself, right? It's only got one electron. So what's it going to do? If I have hydrogen, right? Is it happy with one valence electron? No, how would it be really happy if it had two? Well, in any solution of anything, you don't just have one atom of something, you have a ton of them, right? So if I have two hydrogen atoms like this hanging out, what are they going to do? They're going to create a bond, right? So how would you write this molecule? H2. This is called a diatomic molecule. Okay. All right. So we're going to react it with hydrogen, and we're going to form the sugar alcohol D-sorbitol. Okay, so what's happening as you go this way? Can you tell me about electrons? Do you see pluses and minuses? No, so you can't tell me about electrons. What are you going to end up telling me about? Either oxygens or hydrogens. So tell me what happens as I progress from reactants to products. Am I losing hydrogens or gaining hydrogens? As I go from reactants to products, I'm gaining them. Because what this reaction is showing me is I started with one substance, D-glucose, and I reacted that D-glucose with hydrogens, and I made a product. That means those hydrogens are incorporated into the product. So is this a oxidation reaction or a reduction? If you're gaining hydrogens, reduction. Okay, I'm going to erase A so I can fit in C. Oh. C. The biomolecule FADH2 loses hydrogen, becoming FAD. What are my products? FAD, and what else? H2. So now what happened here as I progressed from reactants to products? The opposite, I am losing hydrogens. So what kind of a reaction? Oxidation. I am telling you that if you don't write down oxidation reduction, you're going to get it confused in your mind. Like even I've got it down. Write it down. It's not a bad thing. It's a good thing. Write it down. Okay. So let's try another one where we talk about identifying oxidized and reduced. So although we mine most sodium chloride, what is sodium chloride? Salt. It can be synthesized by the reaction shown. Identify the reactant oxidized and the reactant reduced. So I'm asked about the reactants. So let's write out just the reactants and talk about what happens. Tell me about sodium in this reactant. I start out with sodium as a solid. Do I have a charge here? No, it has a charge of 0. When I come over here, what is that? That's actually salt. So it's what kind of a compound? It's an ionic compound. By definition, ionic compounds contain ions. Why do I not see a charge? because the charges balance each other out because it's an ionic compound. So what's the charge on sodium in sodium chloride? Right? Remember we said you could do the reverse crossover? So Na is a +1, Cl is a -1. Okay, so now tell me, I have sodium as a reactant. It goes to make a product. What product does it make? Na +1. So what happened to my charge? I went from 0 to +1. So if I go from 0 to +1, what happened? I lost electrons. If I lose electrons, what happened? Oxidation or reduction? Oxidation. Okay, let's do our other one, chlorine. I'm starting out with Cl2. Cl2 gas. Does it have a charge? No, that's a nonmetal to a nonmetal. It's a covalent molecule. What does it turn into? That's 0. What does it turn into? Cl -1. So if I go from a 0 to a -1, as I progress from left to right, what's happening? Am I losing electrons or gaining electrons? I gain electrons. If I gain electrons, what do I call it? A reduction. That's why oil rig is really important. Remember your oil rig. Okay. All right, that'll be good. That'll get us plenty of the way through. How much time do we have anyway? Yeah. Okay, any questions? Exam next time I see you, come with a calculator. Come with a calculator. Please come with a calculator. Anybody need anything on Zoom? Okay, I'll go ahead and end the Zoom.